Good morning, everyone. I request all NRCs please gather immediately. I request Vizag, please mute yourself.
NRC Nandyala. Good morning, Ayana and other friends in Anantapur.
Morning,
Anantapur.
everyone. From KSR Anantapur. Responding from KSR Anantapur. Madam, 1 minute.
Ayana.
Shivaram.
Good morning, అందరికీ మీ అనంతపురం
Good morning. Good
ఎకనామిక్స్
morning, Shivaram.
ఫ్యాకల్టీ అందరికి.
Good morning to all NRCs participants.
హలో.
Morning. Good morning.
Good morning,
Can you-
everyone.
Yeah, you can hear all of the group.
Good
can
morning,
hear me,
sir.
na?
Yes,
Morning,
sir.
good morning.
INS, sir.
Madam, good morning, madam.
Good morning, good morning.
Good morning, sir.
Good morning.
Good morning, everyone. This is Dr. G. INL, lecturer in economics from NRC KSN Government Degree College for Women Autonomous, Anantapur. It is my pleasure to introduce the resource person of this session, Dr. Varghese Kunjapi, CSRD JNU. Today's topic is working with periodic labors for survey data using STATA. Dr. Varghese Kunjapi currently serves as a system analyst at the Center for the Study of Regional Development, JNU, New Delhi. He holds a postgraduate degree in statistics and a PhD in geography, specializing in geostatistical urban growth modeling. He has various professional diplomas and certifications in software applications. Dr. Kunjapi imparts knowledge in quantitative methods to MA geography students and leads training sessions and laboratory practicals to MA and PhD scholars, mainly focusing on statistical software like Stata, SPSS, and R. Proficient in GIS and remote sensing applications, he adeptly utilizes ARCGIS, QGIS, ERDAS, and IDRIS software. His extensive experience encompasses data extraction, management, and analysis of significant survey datasets, including the Census of India, Economic Census, National Sample Survey, and National Family Health Survey. Among others, Dr. Kunjapi shares his expertise through lectures and workshops on data management and analysis using software across various universities and institutions in India. He has contributed to academic journals with research papers and authored chapters for policy reports in the realm of development planning. I will ensure that all the participants would benefit from your insights of this session, sir, and we welcome you, sir, for this session. Thank you for giving me the opportunity.
Thank you. So, today, in fact, I was supposed to talk about the periodic labor force survey data, but then some request has come that, to talk about the data analysis and its interpretations, right? So I will I just made a presentation, and through that presentation, I will give you some idea about how, what are the various ways in which, you can analyze your data as well as you can interpret your data. So, can you see my screen?
Yes, sir, it's visible.
PowerPoint?
Sir.
PowerPoint is visible, no?
Yes, sir. Yes.
Okay, so
Yes,
I'm
sir.
just deviating a little bit from PLFS data. Let us see if I get time later, and then we can go to that. But in the last class, what we have discussed is, from a raw data, how you can create indicators and do certain kinds of table generation and all. Now, I will just talk about, because you should also understand what are the sources of various databases. In Indian statistical information, what are the sources? One is that the Census of India, you can freely download the data and you can do a lot of analysis, as well as, that is handled by the Ministry of Home. Whereas you have a large survey data, which is comes under the Central Statistical Office, under the Ministry of Statistics and Program Implementation, and data such as the economic census, national sample survey, periodic labor force survey, annual survey of industries. These major 4 surveys, data are freely available. The unit level data of economic census, NSS, periodic labor force survey, annual survey of industries, these are freely available in the Ministry of Statistics website. Now the government of India is having an open data sharing policy, a national open data sharing policy, through which you can easily download. Earlier, there was a time when I also used to purchase the data from the ministry. Now it's free. So there is a website called microdata.gov.in. So if you go to that, microdata.gov.in, you can download the data you want. Then there are data like NFHS data, National Family Health Survey. It is basically the DHS data, which is conducted all over the world, and the Indian data is known as National Family Health Survey, which gives you data about the information about the health of women, especially in the women of reproductive age group of 15 to 49 age, as well as there are information which is given about child vaccination, child health, etc. There's another survey called Indian Human Development Survey, IHDS. This again, you can download free. All these data are freely downloadable. Yeah, this is the data source. Now, once you get the data, what you are doing is, first thing you need to do is the data manipulation, a part of which I have already told in the earlier class, that when you get some data, raw data, you should create indicators, which means that from an existing variable or raw data, you are creating new variables. And if new variables, if you want to show it in a distribution table, then you may have to recode it into a new variable. Then data aggregation, I have already shown you how a large survey data or a district level data, you can convert that into a macro level data or a state level data. And then data sorting, keep and drop observations and variable, which is also very important. Why it is important that certain data set like NFHS, National Family Health Survey, which has got more than thousands of variables, 1,500 variables. So it will be very difficult for you to handle all the variables in a single data set. So your intention may be your objective may be something like, let us say, you are studying about the antenatal care, or you are studying about the vaccination of children. Now, then there you maybe require only a small set of data. You don't need that 1,500 variables or some lakhs of observation. Definitely, if you are doing an all India study, then all observations are required. Observation means number of rows are required, but the variables may not be. All the variables may not be required. So you can keep variables Or if there are, let us say, 100 variables are there, if you want to drop 5 variables, you can do this. So those things comes under data manipulation, and as well as query-based analysis. Always remember that Stata is very powerful in the sense that you can do a lot of queries. Okay, so all these are part of data manipulation. So one is that obtaining the data from a reliable source, and then how you can do various kind of data manipulations. And then what else? Then the most important thing, what to do with the data. So you remember this data I have created. I have made 2 or 3 changes. No, you remember this, that I have created around 8 variables. Okay, that day, if you remember, state-wise, that this is the percentage of household with 3 or more rooms, and this is percentage of household with safe drinking water, the percentage of households having latrine within the premises, and then we have created variables like percentage of households having LPG for cooking, and then we have created what is the average percentage of households having 4-wheelers in each of these states, and then we have calculated the sex ratio, literacy rate, and percentage of other workers. Okay. Now what I did, if you can see, there was only this state ID and these eight variables. Now what I have created is one variable called region. Just to save time, I have created it. Okay. So region is one that, I have grouped them into 4 regions. Okay. Region of north, south, east, and west. Right. So what are the, states which falls in the southern part of India or the northern part of India? So these are basically a categorical variable, or you can say that it's a nominal category, right? And then there is 2 more categories I have made, like, just as an example. One is that, percentage of households with 3 or more rooms. I made it into 3 groups of low, medium, and high. So which are the states where the percentage of 3 rooms or more is less? Which are the states? Or medium, which are the states? Or where high? So which are the states where there are higher percentage of 3 rooms and more houses? Okay. And then I have, in a similar way, I have, categorized the literacy rate also as low, medium, and high. So these are the only 3 variables I added to our previous, calculations. These are all, if you remember, we have calculated all this live through a live demonstration in Stata. Okay. Now, what to do with this data? Okay. Wait, yeah. Now, there are many different kinds of, interpretations or inference from the data can be made. There is a visualized way, graphical representation. Through graphical representation also, we can make some kind of inference, or through tabular form. Now, when we call graphical interpretation, and the difference between this and tabular form is that, through, seeing something, we can quickly make some kind of inference, although it may not be that much precise as compared to the tabular, table interpretation. Okay, but here it gives you a bird's eye view of the situation, and there are many ways in which you can, there are many different kinds of graphs available for different purposes. Say, for example, you have box plots, histogram, bar gram, pie chart, and scatter diagram, which are used for different purpose. In Strata, complex graphical forms, like unlike in Excel, you can create graphs by giving the range of data, and you produce some graphs. Here, complex graphs can also be generated. For example, if I want graph by different region, say, let us go to each one of those graphs. Okay, an example I am just giving using the given using the data which we have already created. So first one, the box plot, or it is known as the box and whisker plot. Okay. It's basically a diagram which is used for understanding the dispersion in the data. Okay. Whether it is skewed, distribution, okay, positively skewed, negatively skewed, or it is a normally distributed data. Okay, basically, the box plot is used for finding out the dispersion in the data. Now, how do you do that in Strata? It's very simple. Graph, any graph, remember, in Strata begin with graph. Okay. So graph, then you have to give the command, to what type of graph. Let us say graph, then I type box, which means that I want a box and whisker plot of the variable or the indicator which I have created, that is percentage of households having 3 or more rooms. And then I have 3 different ways of writing commands for different type of graphs. So for example, box plot, if I say simply the variables, it will just create one box. Okay, whereas here graph, box, the percentage of household having 3 or more rooms, comma, over region. Okay. So over region means basically by region I want this box plots. Okay, now if I want, based on 2 different variables, I want to create box plots over region, that also is possible. So basically graph, box. Now what are the variables here I have taken? One is that 3 rooms or more, the other one is the percentage of household having safe drinking. SDWHS means the percentage of household having safe drinking water. So if these two, for these two cross boxes, if I want to make, and I have to give the command like this and then say comma over region. So what I am getting is this kind of graphs. If the first one, if I say graph only that percentage of 3 or room, I will get a single box where it's highly very moderately it is skewed. It's supposed to be, for a normal distribution, it is supposed to be within this box. The line which represents the middle is the median, and the width of this, the width of this, the width of this, end, and the other end is supposed to be 25%, 25%, 25%, and 25% if it is a normal distribution, right? So if here there is a larger gap, which means that there is a slightly more dispersion in the data towards the end of the data. Okay. So, and here you can see the same box plot what I have made, for each of that regions. For north, see, if you give comma over region, then it will create box plot for different taking different regions. So there we can understand, in terms of the percentage of 3 or more rooms, which region has more dispersion in the data. So the west is having less dispersion in the data, okay? Whereas you can see a dot here. dot represents an outlier. Okay. So which is, in one value is, the percentage of 3 or more rooms are more, is an extreme value, you can say. Okay. So probably this will be Mumbai, because West, Maharashtra is also considered in the West, right? So then South, it may be Maharashtra West. Okay. Now South, this is a distribution. Okay. So see the lowest 25% is highly concentrated. That is why this whisker is not even seen. Okay. And whereas there is a larger dispersion in the third quartile, in the third quartile and the second quartile. And the same graph, if I want for north, if I want two box plots, say one for that 3 rooms and one for the safe drinking water, I can do like this with the graph box that take the 2 variables and comma over region. So region wise also, you can add multiple variables here so that, within one region, you can get as many box plots you want. Now, histogram, good thing about, strata is, you can get histogram is not is a simple, rectangular graph. But here, the good thing is that you can draw a normal curve also. Okay. So if you say histogram, percentage of household having safe drinking water, I want the frequency and the normal curve. Okay. Or the next one, I have given histogram, percentage of safe drinking water, comma, by regions. See, in the previous command, I used over command. So depending about the command, slightly this changes. So by region and over region, both will give you the same result. But with certain command, you can use over only, but with certain command, you use by only. Okay, so here I brought by region, and then I want to have a normal. So what I will get is, it will draw a normal curve, and then you can see the different, histogram here. Okay, and here this type of graph is not possible in Excel. Creating in one single graph, creating one for west, one for south, one for north, the other one for east. And then it's normal curve. Okay, so for now, again, the status, graph will be saved in a .gph file. So .gps file is unlike Excel. Excel, whatever you do will be in that particular Excel sheet only. Okay? Whereas here, the moment you create a graph, the graph will be saved as a .gp a file that is that can be edited for, say for example, if I don't want this here density, I can give a descriptive name. For example, here I don't want per underscore SD. I want to write the percentage of household having safe drinking water. So all these editing can be done in the graph editor in the strata. Now, bar graph. So many types of bar graphs. So the first one is not that difficult, because in Excel and all you can easily get it. Graph, let us say, when you write bar graph, you want to make a bar graph, say graph bar, and then let us say percentage of Latin within the premises over region. Okay, here we write over region. Now, which basically means that by region I want to find out this graph. And then graph bar, percentage of household having safe drinking water and Latin facilities over region, and I can take 3 variables, I can take 5 variables, etc. like this, and then if I want to calculate it by region, it will calculate by region. So all these will look like this, you know. See, one is that there was a single variable. The next one I used 2 variables. Okay, so you can see the blue one is the mean of percentage of household having safe drinking water. And this red one is the percentage of household having, mean of the percentage of latrine within the premises. Okay, so if you are taking 3, so that legend is given here, and you can always modify the legend by giving a appropriate name, and title also, then X label, Y label. So there are various types, and then fonts also can be corrected using the graph editor window. Now, if I take, let us say, 4 variables, so it will create 4 for each of these regions. Okay. Maybe this can be, this bar graph you can manage in Microsoft Excel also, if you put the data in that way, right? Now, pie chart, and pie chart is also, I think, Excel pie charts are good. Here, I'm just showing how you can do a pie chart. So graph pie, and then take the variable over region. Okay. Now, if I want to display the name of that region in the pie chart, then I have to use a command also as p label within quote underscore all name. Okay. And then if I want to show the person, so you say p label within bracket underscore all percent. Okay. So if you do so, so what you are getting is the same graph pie chart, but here the south, north, east, west is written, and here the percentage is written. Okay. So if you want both, you can write again p label under within bracket underscore all name. So those things can be done. Now, when you come to scatter plot, basically scatter plot is an analytical graph where you can see what it will do is it's basically used for absolute or indicators or the ratio scale variables to see the relationship between them. Okay. So looking at the scatter plot, we can identify whether it is a positively related or a negatively related or a relationship is not, maybe 0 or there is no relationship. Okay. So positive relationship, the variables, which means that basically it means that, when one variable increases, the other variables also increase. So for example, as an example, age of a person and the height of a person. So which goes, as the age increases, height also increases up to within a limit. Okay. Now, similarly, negative relations, for example, age of a car, age of a vehicle, as the age increases, the reliability or the vehicle's performance decreases. Okay. So as the age increases, the reliability of the vehicle decreases. It's a negative relationship. But whereas, if the scatter plots is very scattered like this without any pattern, then we say that there is no relationship. Okay. Right? So how do we do that in Stata? Okay. So scatter plot is, you can say that graph for scatter plot you have to write two-way scatter and then the variables. Now the first variable you are giving should always be the vertical variable, which means that the dependent variable, or you can say that basically the y-axis, whatever is in the y-axis should come in as the first variable. Okay, and the next one is the horizontal axis, is the X variable. So in the case of a regression, the first variable will be the dependent variable and the second variable will be the independent variable or the predictor variable. Okay. So graph two-way scatter, this gives you a scatter diagram like this. Now here again, instead of over, I used comma by region because graph two-way accept by only. So by region. So this may not be possible in Strata to create such kind of graph. Okay. So you can see from this scatter plot, there is a correlation, definitely, because I can see there's a correlation, but that correlation is not that much high. So there's a positive correlation. As literacy increases, the chance of having the four-wheelers are also high, or the percentage of four-wheeler households also go up as the literacy rate or the education increases, right? Now, when it comes to different regions, you get the north is having more, positive relationship than the other one. Also, the other one also having, slight, very, insignificant positive correlation. It's not negative correlation we can see from this data. Right? So this is how you can draw the scatter plot. Now, if you want a scatter, if you want to fit a regression line or the line fit, that also can be done very easily in Strata. Okay, so what you do is only one thing more, graph two-way. Only thing you have to write is L fit. Basically, the regression line fit. The command we use is L fit. That is should be within bracket, and then the variable names. That is the percentage of four-wheelers, percentage of household having four-wheelers, and the literacy rate. And the same variable you have to write within comma scatter those two variables, and then you write comma by region. So it gives you the line also. Okay. This is basically the regression line. Okay, so you can see that all are slightly, positively related, but these are very insignificant relation, whereas this one is having a better correlation out of these four regions. Okay. Now, as I said, that to save any graph using this command, you have to say graph save graph. So this is important. If you want to save this graph after doing all that editing, either you go to the file and save, or you can say the parallel command is graph, then save graph, and then here you write where do you want the file to be saved. That's what I just wrote path. You can say C drive or F drive or C drive desktop, whatever folders you want to write here, you can write, and then what file name you want to give, you can give an appropriate file name here, and then you give .gph. Okay, so it save it as a graph. GPH is basically the short form of graph. Okay. Now, these are basic graphical representation of the data. Okay, so I basically told about the box, the histogram, the bar graph, the pie chart, and the scatter diagram. So there are some other special type of graphical representation. Say, for example, age sex pyramid, which is not a general graphical method. So therefore, you may not find it in Microsoft Excel, but you can find it in Strata. Okay. So special kind of graphical forms are there, which you may not be available in Excel, but it can be easily done in Strata, and you can combine one or more categorical variables. Say, for example, I want region-wise or something else. Say, for example, region-wise as well as rural-urban wise. So I can write two different by region and then by let us say sector, whether it is rural or urban. So a complex graphical representation can be done through strata commands. Okay. Then when we come to the tabular form of statistics, there are broad two kind of statistics. One is descriptive statistics, okay, and the other one is the inferential statistics. Okay, so what do you mean by the descriptive statistics? So anything which describe a particular data is a descriptive. So for example, through a frequency, just finding out the distribution in the data, which one is low, medium, or high. Okay, that is frequency or cross table. Suppose I have the categories of the literacy rate, and I have the categories of the region. So through two different categorical variables, how I will find out the distribution of a third variable, which can be done. Okay, then various central tendencies. Central tendencies basically mean that which is a single value which represents the distribution. The most appropriately represents the distribution. Okay, so mean can be one, median, mode. These all are central values, which represents a set of data. Okay. Then various dispersals can be found. Okay, that means how much variance or standard deviations are there in the data. Now, the only thing is you need to remember that when you talk about dispersion, there are two kinds of dispersion. That absolute dispersion and relative dispersion. Okay, so when you are dealing only with a single indicator, so the absolute dispersion gives you what is an example of an absolute dispersion? Standard deviation. So you can calculate standard deviation, and based on the standard deviation, you can say whether the data is having consistency or not. What is consistency? Means the dispersion and data is less or larger. Okay, so more consistency means less variability in the data. Okay, less consistency means there is a high dispersion in the data. Okay, so if you are having a single variable, then it is okay to find out the standard deviation and decide how much variability is there in your data. But when you are comparing two districts or two states, say for example, I want to compare two variables of a state, let us say literacy rate and sex ratio, and let us say all India. I want to compare. So how, which is more consistent, the sex ratio or literacy level? What does it mean? Consistent sex ratio or literacy means whether sex ratio is having less variability or the literacy rate is having less variability. So if you are comparing, then the relative dispersion comes into picture, which means that you need to find out the coefficient of variation, okay, or what we call it as the CV. Okay, so CV of a data is basically, is calculated. How do you calculate the CV of a data? CV is the standard deviation divided by mean multiplied by 100. Okay, so one reason why we calculate the CV is, the variables are also having different units. So for example, sex ratio is calculated out of 1000, and the literacy rate is calculated out of percent. So the units, or if you are suppose, let us say we have another variable called the percentage of Pakka roads. How many, or the number of kilometers of Pakka roads in a particular state. So these variables are having different units. So once you convert that into CVs, that it becomes unit free, and then it will be very easy to compare. So therefore, we call such measurements as relative measurements, which means that you are comparing between two groups. Okay. And then these are all, single value-based statistics or descriptive statistics. Okay. But when it comes to inferential statistics, which means that, you are making out inference based on your data. Okay. So which means that you need to perform some kind of statistical test. Or if you are finding out whether two variables are correlated. Basically, if you are using a sample and you are finding out correlation is significant, which means that you are making some observation about the population also. Okay. So you are saying that there can be a correlation between the population variable, respective population variables as well. Okay. So that is basically inference. Inference making the inference about the population. Now, we can do linear regressions to estimate the model statistics, and then we can calculate binary logistic regressions. Basically, the binary logistic regressions are based on categorical variables. So if you are having dichotomous variable, binary means the variable having only two values. Say, for example, rural urban is a binary variable, okay, because male female is a binary variable. So binary logistic regression means the dependent variable in that particular data will be a dichotomous variable or a binary variables. Okay, so such logistic regressions can also be done through Microsoft. Through Stata. Okay. Then suppose you want to find out the 95% confidence interval for me of what type of command you can use now. What does a confidence interval means? See, when under repeated experiments, or when you select a random sample from a population, how likely that the value falls within a particular range. So that is the confidence interval. Now, you see, I have given a command here that CI, that stands for confidence interval, CI SR1. SR1 is a variable, you remember, that I calculated as sex ratio. Okay, so CI SR1. Okay, so if by default, if I say without any level, if I specify, it will calculate a 95% confidence interval. Okay, so CI SR1, which then it will give you this result, where it will say that the sex ratio is having 35 observations, which means that 35 state of union territories were there, and the mean of the data is 931.22. The average sex ratio of India as per our data is 931.22, and the standard error is 13.5. How do we calculate standard error? Standard error is the standard deviation by under root of n, sigma by under root of n. So it's not standard deviation and standard error same. Standard error is standard deviation divided by the square root of 35. Okay, right? Now, and then the 95% confidence interval it calculated when I gave this command is 903.78, and the upper threshold is 958.6695. Okay, so which means that if you randomly select any state, the sex ratio will 95% chance is that the sex ratio will fall within this particular limit, 903 to 958, given this data set. Okay, given this variable. So it's calculating based on this variable only. Okay. Now, if you want to find out a 99% confidence, definitely this interval will be larger. So our confidence will increase when your value, the limit also get increased. Okay. You understood what I said? Now here it's a 95% confidence limit. Now if I want a 99% confidence limit, you have to say CI SR1, comma level within bracket 99. So if you don't give this level, it understands it is a 95% confidence. If you give this 99 or 98, you can get a 98 or 99% confidence interval. Okay. So which means that now it means that 99% confidence is there that if you get any data randomly, it will fall between 894 and 968. Okay. Now, if you increase this, let us say that the lower limit is 500 and upper limit is, let us say 1500. So that confidence will be how much? It will be 100% because our data doesn't go below less than 500 and more than 1000. Okay. Okay. So which means that almost every data is likely to be fall within 500 to 1500. That is the meaning of it. Right. So you understood this? So a 90% confidence interval have a smaller interval. Okay. This is about the confidence interval. Now, if I want to find out the confidence interval by region and total as well, I can do. Suppose I don't want to calculate the confidence interval for that particular variable for all the regions taken together, but I want separately for north, south, west, and east. So you can do CI. I have taken a different variable percentage of 3 rooms or more till percentage of 4 wheelers, means from here till here. It means that all the variable starting from percentage of household having 3 rooms till the households having 4 wheelers, then it will calculate from the this safe drinking water, latent facilities, LPG gas, and all these things. Because I have used a hyphen. So hyphen in between means from this to this, because it is in SATA all these variables are adjacent to each other. So I'm saying that from this variable till this variable means all the 5 variables. Confidence interval I want by region. So by region, I have not shown all the values here because of the space. So I have taken region is north, region is east, region west, then we will get the region south. And then because I have mentioned, if you see by region, after that I have mentioned total also, which means that the entire regions. Okay. If I want, so that result I will get, the confidence interval is here. So say 95% confidence interval for percentage of household having 3 rooms are 31 to 42.8 or 43 in the north region. In the north, that is important. Okay. Now, safe drinking water, which is 32 to 75. So a 95% chance is that if I go to randomly select, a household in the northern district, so it is likely that the safe drinking water, the percentage of household having safe drinking water is between 32 to 75%. So this is north, then east. For west, likewise, you can calculate if you give this particular command. Now, that is one thing, confidence interval. Now, if you look at the chi-square test of independence, okay. Now, chi-square test, where do we use? First of all, you should understand chi-square is a non-parametric test. What does a non-parametric and parametric test? Parametric test means if you will be able to calculate the population statistic. Okay. So, which means that the parametric measurements you can do only for ratio scale variables. Non-parametric analysis are done on a categorical variables. For example, nominal category. If you want to see the relationship between two nominal categories, you cannot do a Pearson correlation. It's difficult. It is meaningless because our values are that the category input we have given is based on names only. That is why we call it as a nominal variable. So nominal variable means the variables which is created based on name. Say for example, our region, one is north, two is east. These are just, we have defined one is north, two is, we can always define one is south, etc. So we have given some name for some code. So therefore, it is known as a nominal variable. So such kind of variables where you have you want to find out the association between, is there any relationship between this kind of variables, then you can do a chi-square test. Okay. So non-parametric variables. Like for example, here I have written tab lit cat. You remember I have created at the end two variables. One is literacy categorized, okay, as low, medium, and high. I haven't taken that percentage of literate here because that is an absolute percentage, okay, or it's an indicator. It's a ratio variable. I can't run a chi-square for that particular variable. So I have categorized it into three groups, and percentage of 3 or more rooms also I have categorized, okay, or recorded it. Okay, and then I say, suppose I say NOF, NOF, which stands for no frequency, means I don't want to get the number of states or union territory falls under that, but I want the percentages. Okay, so for percentages I wrote row. So row means I want a row percent, which means row will add to 100. Okay. And then at the end, I type CHI2, which is basically means chi-square. So what you get is a table like this, in which you have the percentage of 3 or more rooms categorized as low, medium, high, and the literacy rate also categorized as low, medium, and high. Now, what is this 50 means? There are 50% households having very low literacy rate, okay, as well as the percentage of 3 or more rooms are very low, okay, which means that there are very few 3 or more rooms are there in this category. Okay, so this is basically a cross table. Okay, so what does this mean? This means that the percentage of 3 or more rooms and the literacy rate is high, is the intersection of this is 28.57%. So 28.57% of households are having high literacy rate as well as more than 3 or more rooms. Okay. Now, and then based on that, a chi-square test statistics is calculated. So the value of that Pearson chi-square is 4.12. You know that the chi-square is calculated how? That is there is a statistical formula with summation O minus E the whole square by E. That is observed frequency minus expected frequency the whole square divided by E. So using that, it calculated 4.12. But you should remember, I'm not going into testing of hypothesis, all those things. It will deviate from the purpose of this class, because that will take more time. So here I just want to only say that whenever you do test something, there is a null hypothesis and alternate hypothesis. Okay. So here also, when you are finding out a chi-square, there is a null hypothesis. That null hypothesis is that there is these two variables are independent. Means there is no association between the distribution of the 3-room households and the distribution of the literacy. Okay, so these are, so we are saying that we are setting a null hypothesis that these two are independent of each other. Means having 3 or more rooms is nothing to do with the distribution of the literacy rate. That is our null hypothesis. Okay. Now, accepting or rejecting that null hypothesis is based on this probability. Okay. So basically, this probability means the probability that the calculated test statistics falls within a critical region. So you don't have to see. It's an easy way how to understand this is, if this value 4.12, whatever be the magnitude of this value, this PR is important. If it is 0.05 or less, remember, if PR value is 0.05 or less, what we do is we reject our null hypothesis. We reject this is very important. Okay, so we reject our null hypothesis. Okay, but here the value is higher than 0.05, means 0.389, which is much higher, which means that we accept the null hypothesis, which means that the distribution of the literacy rate and the distribution of 3 or more rooms is independent of each other, is not associated. Okay, maybe you can find some kind of association when you do region wise. So as a whole, it is not having any relationship. It will not give you, remember, chi-square will not give you the strength of the relationship. Unlike, in the correlation, it gives you whether the correlation is highly significant or significant at 1% or etc. So more related, or looking at the value, if it is going towards more to 1, you say it's a very high value of correlation coefficient, there's a strong relationship. So those kind of things you will not get through this chi-square. It only will say whether these two variables are having association or not. Okay. Now, when you do a t-test, okay, so t-test in Stata is very easy. Okay, so just have to write t-test, just like the name.
Sorry to interrupt.
Yes.
So sorry to interrupt. So regarding chi-square test, if the value is less than 0.5.
Yes, then we are
rejecting null hypothesis.
The null hypothesis.
That means there is no significant
null hypothesis. What does rejecting the null hypothesis means? What was your
there is no
null hypothesis? That there was no relationship.
So that means we are rejecting the null hypothesis.
Sorry. I told in a different way. Okay, just
yes, sir.
Yeah, that's true. Rejecting, but here you are not rejecting, na? Here you are not rejecting. I told correctly. Here you are not. I said if the value is 0.05 or less, means 0.01, 0.02, etc. Then only you reject your null hypothesis. In this case, we accept our null hypothesis. What was our null hypothesis? That there is
no relationship
between the distribution of two variables. I would say distribution because low, medium, high, we redistributed the data. Okay. Got it?
Sir, if it is, sir, if it is 94% of confidence level only, then we are going to prove this, that is,
Yeah,
if the
yeah, yeah.
value is less.
That is definitely it happens, you know. Significance level and confidence interval is just opposite to each other. For example, 0.05 significance level means 95% confidence level. 1% significant level means 99% confidence level. Okay.
Okay, sir. Okay, thank you, sir.
So now you come to the t-test. The t-test can be, there are three different kinds of t-test. One is t-test with a constant value, means you are finding out whether a constant value is significantly different from a sample mean. So for example, I have a variable called, let us say, literacy rate. Okay, I am saying that I am giving a hypothesis that the average literacy rate is equal to, let us say, a constant value of 70. Okay, that 70 is just, I'm just hypothesizing. Okay, now which more often you will not be using this one, but I'm just saying that there are one-way t-test, one sample t-test is there, then t-test based on two variables are there, t-test based on categories are there. The second one is more important. Okay, t-test literacy rate if region equal to 1 or region equal to 4 by region. Now, why I don't have to, basically you understand that t-test is done for two groups. So if more than two groups are there, the t-test will not be performed. Therefore, then what we will do? We will find out an ANOVA, okay, analysis of variance. Now here, why I use this if is basically because of one reason, because the region is having 4 different values, 1, 2, 3, 4. Had it been only 2 values, then I don't have to use these if things. Here, just to show the result, what I did is find out the whether there is any significant difference in the literacy rate between the northern region and southern region. Okay. Now, for that, now you will get only 2 values in the region because I have limited the analysis only for 1s and 4s. So then it is okay, t-test is okay. But with more than 2 values, t-test will never calculate anything because it is not meant for more than 2 categorical values. Okay. Now, if I say t-test literacy rate 1 if region equal to 1 or region equal to 4 by region, what result you are getting? See, this is for the first one. The first one, if t-test literacy rate equal to 70, here the null hypothesis is that what? Is that the average literacy rate equal to a hypothesized value of 70. I'm saying this is just, I gave a value 70, 68, 90, whatever value you want. Now it will test whether the sample or the average literacy rate we have in our data, whether that and that particular constant value are significantly different or not. Okay. So here it's you can see that the probability is, in fact, probability will never be 0 in the mean. In fact, it gives only 4 decimal places, 0.0000, maybe 1, 2 can be here. So it gives up to a, which definitely means 99.999% confidence. Okay, which means that when, as I said, as a thumb rule, anything below 0.05, we reject the null hypothesis. So null hypothesis was that there is no difference between the constant value and the average literacy calculated, which means both are same. But we are rejecting it because of this fact that it is less than 0.05, even less than 0.01. So it's a highly significant value. So which means that there is a significant difference between the average mean, which is what was that 77.91, and the value 70 is statistically highly significant, means that is not by chance. Okay. So there is a difference between these two values. Now, if you look at the t-test, the one command which I have given after that, that's the t-test literacy rate one, if region equal to 1 or region equal to 4 by region, what you are getting is you are getting the north and south region. Its mean is given. Now, what is the null hypothesis there? That the average literacy rate in the northern states and the average literacy rate in the southern states are equal, or there is no difference between the average literacy of north and south. And here, again, there is, the north, the literacy average literacy rate is 74.32, and the southern states, the average literacy rate is 83.67. So you got 0.0333 as the alternate. Now, it all depends upon, what do you want to see? Difference, there can be one tail, there can be two tail. Okay. So if the, first one is less than the second one, or the second one is depending upon that, you will get three values. Now, you just don't have to look at that. Here you know that north is, the mean is 74, south is 70. Obviously you can see that south one is higher. So you just see this one, the alternate hypothesis two tail. So its probability of this is 0.03. So as I said, that if it is below 0.05, it is highly significant, which means that there is a significant difference between the literacy rate of north and south. Okay, so it is not same. So statistically, there is a significant difference between the literacy rate of northern India and the southern India. Now, when you look at ANOVA, now ANOVA is analysis of, also its name is analysis of variance. Here also we are looking at whether there is any significant difference in the mean between the groups. Okay, definitely the variance will also becomes higher if there is significant difference. Okay, so if the means are higher, having a high difference, which means that if you the square deviation also will be higher. So therefore the variance also will be higher. Okay, so that is why it is given the name analysis of variance. It provides another way of more general than the t-test to find out whether there is any significant difference in the means. Now here you can use more than two categories. So if I say one-way literacy rate region tabulate, now here one-way, say one-way analysis of variance and of the literacy rate, and then space region. The second one is not a ratio scale variable. It has to be a categorical variable. It means you are finding out the average significant difference in the literacy rate by the region, by north, east, northwest, all those things. Okay, 4 regions. Now, if you look, if you use comma tabulate, that is an optional command. Anything after comma is an optional command in Stata. Okay, which means that it will work. The command will work even if you don't give that comma tabulate. Okay, so here the comma tabulate will, what does it calculate? The tabulate option produces a table of means and standard deviation in addition to the ANOVA table. Okay, now a two-way ANOVA is there. That means, of as variable. Say, for example, I want to see whether the average, percentage of household having 4-wheelers are significantly different with respect to the region as well as the category of literacy. Okay. So these two are categorical variables. And the interaction effect also can be done. A 2-factorial interaction also can be done If you type region, then in Stata, you have to type hash sign only for interactive effect. Okay. So if you do this, so it will generate. So the first one-way literacy rate region. So between group, within group, sum of squares are given. And then the important thing is that the value of F. Okay. So here it is not below 0.05, which means that, what does it mean? The calculated value is less than the table value. Okay. So if it is below 0.05, we could have rejected it, but in this case, we have to accept the null hypothesis that between the group, there is no significant difference between what was the literacy rate. Okay. Literacy rate do not vary across. If you are comparing only two, you may get something, but if you are comparing all the between sum of squares you take, so it says, there is only a marginal difference, there is no significant difference. Okay. Now, if you look at the ANOVA, now percentage of household having four-wheelers by region, literacy category, and then the interaction between these two, you can see for all these, the model sum of squares is basically the regression sum of squares. And now here the between group sum of squares means the regression sum of squares. Within group is the residual sum of squares. If you add these, you'll get the total sum of squares. Right? So I'm not going into detail of all those things. Here you can see that each F value is important. Now here, in all these cases, I can't find anything which is the probability is less than 0.05, which effectively means that the table value of F is less than the calculated value of the test statistic is less than the table value. Then okay. So in that case, what we do, we accept the null hypothesis. We accept the null hypothesis. That means there do not exist any significant difference in the percentage of household having four-wheelers across regions, across literacy category, or across region and literacy category. So this is how you can perform, one-way and two-way ANOVA. See, if you, here you write simply ANOVA. ANOVA means performs a two-way ANOVA. Okay. If you want a one-way ANOVA, you just have to write one way. You don't need to write ANOVA, just write one way. So it will automatically understand you want to calculate, ANOVA T. Now, when it comes to correlation, okay, now correlation is basically a quantitative, method. Okay, so Pearson correlation coefficient is a statistical technique which is used to determine the degree of relationship between the variables. So one way of finding out the crude way of measuring the scatter plot, the correlation was through the scatter plot. Looking at the scatter plot, you can make an assumption, okay, it's a positively related or negatively related, etc., or there is a relation, there's a no relation, etc. But how we measure it, okay, is through a correlation coefficient. So correlation coefficient is again a statistic which shows the degree of relationship between two variables. So basically, what does it mean? How do you calculate? The statistical formula, it's the covariance of the variables divided by what? Divided by the standard deviations. Okay. So standard deviation of both the variables. So individual standard, sigma x into sigma y. Okay. So and correlation ranges from -1 to +1. Okay. Now, if you don't want the covariance, you want to calculate the correlation, you want only the covariance, Stata has an option, just put comma covariance. So it will not write the correlation, it will only calculate the covariance. So you know that covariance is calculated how? Summation xi minus x bar into yi minus y bar divided by n minus 1 or n. Okay, so whatever, if it's a population covariance, you use n. If it is a sample covariance, you use n minus 1. Now, correlation, how do you correlate the percentage of households having 3 rooms to that hyphen I have put. Now here you see I have put a hyphen, means up to the percentage of other workers. Okay, percentage, the average percentage of other workers is this one. So all the 8 variables, including that, I want to calculate a correlation table. I can do that. Now, if I want a pairwise correlation, PW correlation is basically meant as pairwise correlation. So that is that I have to, what does pairwise correlation correlate means? Correlate has a case-wise deletion. Pairwise correlation is only that pair. If one value is missing, then it will not be included in the correlation. Whereas the case-wise deletion, which means that if how will I say that, let us say 2 variables are there, okay, one is having 10 observations, the other one is 5 observations. So it will, that missing observations case will be deleted from the entire matrix. Not even if the other variables are not missing, the entire row will be deleted. But here in the pairwise, only that pairs will be compared. First of all, if you are looking at, let us say 3 room is is correlated with the literacy rate, only that pair is compared. If any missing, that will be deleted. Otherwise, it will be included. So the both the way you can see that correlate gives you a result like this. Okay. Since all our value, our data has no missing value, so therefore it is the value of these 2 will remain same because we don't have any missing value. So whether it is correlate or whether it is pairwise correlation, so both will. So you get a matrix here. Okay. So now here you see the diagonal elements are 1. Now because of the space, the last one, the other workers is brought on down. Okay. It has to be, in fact, it should have been came here. Okay. The last one, but because of the space, I brought it down. Now you can see we have used here comma star 0.0. I could have used star within bracket 0.05 also. So what I said here that mark all correlation with a highly significant level of 1%, or mark all correlations having a 99% confidence. Okay, so which you see that some are marked automatically because I use this star within bracket 0.01. Okay, if you do a normal correlation, you cannot do this optional command is not there. So always between these, the better command is pwcore, because you can get in the table, you can get the significance level also. You can see that 0.4842 star here, which means that the correlation between the percentage of household having latrine facility and the percentage of household having 3 rooms or more is very high, which means that as one increases, the more likely that the other one also increases. You see, there is a very high correlation, that is 0.8145. So, which means that it's a highly significant one, which means that it is very highly likely that a household having safe drinking water facility also have LPG facility, which means that as the safe drinking water facility increases, the percentage of household having LPG also increases. Okay. So in a similar way, you can analyze this. The one which doesn't have the star, which means that you can just say that it's a positive or negative, but you can say that it is insignificant correlation at 1% level. Okay. Now, if we go to linear regression, I don't need to give you what is a linear regression. You know that in the linear regression there will be a dependent variable and there will be more predictors variables or independent variables. So, and it gives you a relationship of y is equal to, or your dependent variable as a function of many independent variables plus a constant intercept, or we call it as a y intercept plus an error term, and error is a normal distributed variable, right? And where beta, this beta 1 is the slope of the equations. Okay, what is slope? It is basically the change in y with respect to the change in x. So a unit change in x, how much change it makes in y is interpreted through the beta coefficients. Okay. Now, if you do now, how do you do a linear regression? Is regress. The command is regress. So you write regress, then the variable, which are the two variables. I want to do a regression, keeping the percentage of household having four-wheelers as the dependent variable. And I say that the percentage of people who are working in secondary and tertiary sector are a determinant of the people who are having four-wheelers, which means that they are highly skilled job workers. Therefore, they can have affordable to buy four-wheelers and all. So in that case, so it will be very important to choose the dependent. Always you put dependent variable at first. So otherwise, Stata will take the first variable as the dependent variable. Okay. Now you can give more variables here. So anything more than that will be, suppose you can give 4, 5, 6, 7, 8, as many as number of predictor variable or independent variable. So it will calculate the beta coefficient for each of that. Okay, so what is the command? Now, if I want specifically regression for only the northern region, then I can do the same command. You just have to say query based analysis. If region equal to 1 means north, 1 stands for north. If region is northern, then find out the same kind of regression analysis. Now, there can be other things. You can estimate the estimated value of the y. The estimated value of the percentage of household having four-wheelers is in fact it's not an independent command. Remember, predict is not an independent command. Predict always happens after you give a regress command. Otherwise, it will not work. Okay. So if you want to predict the estimated value of y, then you can, after giving the regress command, you can do a predict y cap, y estimate. Y cap simply means y estimate. Okay. And then if you want to, the error terms, if you want to predict the error terms or calculate the error term, it is the difference between the actual value of y and the estimated value of y. So if you want to do, you just say predict E, RESID, residuals. So it will calculate the predicted value of this. So if you do this, I have calculated the regression here. Now here you see there are two R square is there. R square is basically the percentage of variance explained. Okay, percentage of variance explained. Now what does that mean? Now there are two things. R square is there, adjusted R square is there. So if the number of observations are more and the number of predictor variables are less, R square and R adjusted will be more or less close to each other. But if you have the number of observation less and your predictor variables are more, so there is a chance that the R square will be, overestimated. So in order to avoid that overestimation, so we have an adjusted R square. So you should interpose the explained variance based on the adjusted R square rather than R square. So what does it mean? 0.31 means there is a 31% variance in Y in the percentage of having household having four-wheelers is explained by the percentage of other workers. So other worker explains 31% variation in the percentage of household having four-wheelers. So that is the meaning of that. How much?
So can you repeat the relation between?
It means that the variation in dependent variability in the dependent variable. How much? What is the contribution of other workers in explaining the variance in your dependent variable? So in a way, you can say that 31% change in your household, four-wheeler households is explained by the percentage of workers in the other categories. Okay. So which means that that's a substantial number. What is why it is 31%? There can be other reasons which contribute to the explanation of the percentage of household having four-wheeler. I'm just taking this an example only from our data. Okay, you can do real regression calculation by taking the actual variables you have. Okay, now if I say now whether each of these coefficient is statistically now, there are two different statistics. One F statistic. F statistic basically whether your regression model is significant or not. And here T value means whether the coefficient is significant or not. Okay. So here since only one coefficient which is highly significant because T value is 4.05. So as a thumb rule, any value which is more than 1.96 will be statistically significant. Okay. So, or the modulus of T, if it is greater than 1.96, so the coefficient will be significant, which means that other workers is definitely a predictor variable for this percentage of household having four-wheelers. Okay, so which means that how do you explain this coefficient? Means a unit increase in the percentage of other workers increase the percentage of household having four-wheelers by a factor of 0.16. So if a one unit here, the percentage, a 1% increase will increase the percentage in four-wheel household by 0.15 percentages. Now here, if this is significant, model is also significant because there is only one variable. It's not necessarily that sometimes some coefficient will be significant, but model will be insignificant. Here, there is only one variable. So it has, if this is significant, definitely this also will be significant. Means the model is a correct model. Okay. Now here, this is a one which we have done only for the region 1. Means for northern, now the time is over. For if the northern region is, if the region is north, then what would be the output? So you see the T value even gone up 7.71. So, and if you look at the explanation, 0.854. So 85% of variation in the northern states is depending upon the percentage of people having highly skilled job. Okay, so they are the one who are purchasing the four-wheelers and all. So it's the variation in four-wheelers household 85% is explained by the percentage of household having other work in North India. In a similar way, you can do for other regions as well. So time is over. So I'm just stopping it yesterday because I got a message that I should say something about the interpretation. So that is the reason why I used our own data and then I did some calculation quickly and through a PowerPoint I shown this. Thank you very much. Anything you want to ask? See, I had to.
Thank you, sir. Thank you for your excellent presentation. It's a very useful presentation, sir. Thank you for sparing your valuable time with us, sir.
Thank you.
Chittoor,
Thanks.
NRC Chittoor. Please propose vote of thanks.
Madam, good morning to all participants. I am Dr. N. Venkatnarayana, lecturer in economics, Government College, Autonomous Anantapur. From NRC, Government Degree College, Women, Anantapur. Professor Dr. Varghese Kunjappa, on behalf of Commissionerate of College Education, Government of Andhra Pradesh, I extend my deepest gratitude for enlightening lecture on working with periodic labor force survey data using Stata. Your expertise and passion for subject matter shown brightly throughout the session, leaving us with invariable insights and practical skills. Your clear explanation and engaging presentation style made complex concepts accessible, empowering us to navigate and analyze labor force survey data with confidence. Your dedication to fostering living and skill development is truly commendable, and we are grateful for the opportunity to benefit from your knowledge and experience. Thank you once again for sharing your time and expertise with us. Your contribution have undoubtedly enriched our understanding and equipped us with valuable tools for our academic and professional pursuits. Thank you, sir.
Thank you. Thank you for your nice words. So can I leave now? Can I leave now?
Yes, sir, you can leave now.
Okay. Thank you.
So good morning. Am I audible? Should we start?
Good morning, ma'am. You are audible.
Yes, should we start or wait for 2 minutes?
2 minutes, ma'am. Just wait for 2 minutes.
Okay, fine.
All the coordinators, please ask participants to come back quickly. KRPs, please request participants to come back quickly. Ma'am is waiting. Ma'am, please start your session, ma'am.
Good morning, sir. First of all, I welcome you, sir, to this session. It is my privilege to introduce Professor Indrani Roy Chaudhary, Center for the Study of Regional Development. She got MPhil from Jodha University, PhD from Center for International Trade and Development, JNU. She is specialized in many areas of economics, particularly health economics, environmental economics, development economics, applied game theory, and quantitative methods. Previously, she worked as Associate Professor, Department of Economics, Jamia Millia Islamia, Economist, National Institute of Public Finance and Policy, and Associate Fellow, Council for Social Development, New Delhi. She wrote many excellent articles for reputed national and international journals. Each and every article is a sample of her efficiency and eminency. Thank you. Once again, I welcome you, ma'am, to this session.
Thank you so much. So I'm really humbled. So without losing time, because yesterday, I could not finish the portion which I expected that I should be able to cover. So I just don't want to waste time. But tell me one thing, before I start with the estimation and hypothesis, should I just cover little bit, say around 10-15 minutes on the normal distribution and the T distribution, trying to understand the table through which we can get the values and then estimate the probabilities. Do you want me to do that first and then go to the estimation, or should I just start with the estimation, and if there is some time, then I can explain those things. So whatever is a preference, I will go by that. Hello? Hello? Am I audible?
Yes, madam, you are audible.
Acha. So I just want to know that should I explain the technique for looking at the normal table and then T table and then calculate the probabilities, which I was supposed to do yesterday, but I could not do because of the time constraint. So I was thinking that if I can explain it to you now, or it can be done after, if there is some time, if I can manage some time after the these estimation and the hypothesis testing. So whatever is the preference, I will go by that.
Madam, good morning, madam. Good morning,
Sorry?
madam.
Good morning.
Good morning, madam.
Good morning,
you?
Annapurna. Nice
Sir,
to see
madam,
you.
can you continue? Yeah, thank you, madam. Can you continue the topic which is allotted today?
Okay, fine, great. So I'll then share. Can you see my slides? Can you see the slides?
No, ma'am, no.
No, madam.
Oh, just wait. Is the
No,
slide
ma'am,
visible now?
It's visible. Yes, ma'am, it's visible.
Thank you. So the topic which I am supposed to cover today is the estimation and hypothesis testing. So whatever little bit of probability distribution and the sampling distribution which I explained yesterday is basically to set the background for the estimation and hypothesis testing. And as you know that statistical analysis can be divided into two parts. First is the descriptive statistics. So descriptive statistics is much simpler in a sense that here you don't have to any complications, in a sense that whatever data set is available to you, from that data set through the face value, you can do some analysis. Okay, so like the measures of central tendency, measures of dispersions, you can do with various figures, charts and bars, diagrams. So all these things will give you some idea about the data in the face value. But when you take the inferential statistics, that is basically the more analytical part of statistics. More analytical part of statistics, I mean that here basically you have to go beyond the face value of the data. That means whatever data is available, beyond the face value you're trying to predict, you are basically trying to validate some of the estimations which you have done. Okay, so inferential statistics is much more in that sense analytical, and it deals with not just only with simple generation of numbers. Like in the case of the descriptive statistics, you basically calculate mean, median, mode in the measures of central tendency, or in the dispersions you basically calculate mean deviation, mean absolute deviation, standard deviation, coefficient of variations. So there are different methods which you basically create some or generate some numbers. But in the inferential statistics, it's not just simply generating numbers, it is more of the predicting and concluding about certain claim on the data. Okay, so when we are dealing with the inferential statistics, one thing must be remembered, that here we are more dealing with the population. So just collapse. Yes. So here we are dealing more with the population. That means, as you all know, that population is very, very vast and it is most of the time inaccessible. That means the researcher has very little information about the population, but the researcher want to conclude something about the population through their research. So in order to do that, what the researcher does in the quantitative techniques, they basically take the data which is a sample, which is just a subset of the population. And through the study of the sample, they try to conclude something about the population. So the inferential statistics are actually help you to conclude about the population through the study of the sample. Okay, so these are basically the techniques that allows us to use the sample to make generalization about the population from which the samples are drawn. So it is important that the sample accurately represents the population. So when we are dealing with the inferential statistics, the background, that means the sample design part, which is again a subtopic of statistics, where basically a lot of understandings are developed that how to design the sample so that your sample is a representative sample. That means whatever the diversified characters your population is having, so those diversified characteristics must be present in the sample. If it is not, then your sample loses its representativeness. Okay, and this process is called the sampling. But in the inferential statistics, one more thing is that it is based on the values which are generated from the sample, more precisely from the sample statistics. So yesterday, if you remember, we discussed about the distinction between the statistics and the population. Statistics characterizes the sample like sample mean, sample variance, sample standard deviation, whereas parameter characterizes the population, right? So it is population mean, population standard deviation, population variance. So the sample statistics is used to estimate or to infer the values that would be measured in the population. That means we try to estimate the true value of the parameter through the observations of the sample, through the calculation of sample statistics from the sample which we collect. So there will always be some degree of uncertainty in doing so. Why? The uncertainty is involved because you are not knowing the entire population in totality. You are only trying to understand the population through a very small subset of the population, which is your sample. So you are not supposed to be 100% precise. Okay, so the precision is, you cannot assure, even if you take best of your effort to design the sample, you cannot be 100% precise. Okay, so some degree of uncertainty is embedded in your inferential statistical analysis. But how much uncertainty, that means how much deviation from the true value of the population parameter should be exercised, that is also to be understood through our understanding of the inferential statistics. Now, when we talk about the inferential statistics, basically it deals with two set of problems. One part is the estimation part, another part is the hypothesis testing or test of hypothesis. It is also called the test of significance. Okay, so the objective of the sample is to study the features of the population based on the sample observation. A carefully selected sample is expected to reveal these features, and therefore we can infer about the population parameter from the statistical analysis of sample statistics. Okay, and this process is called statistical inference. Okay, and there are two problems as a set of problems which I already discussed. One is the problem of estimation. What is the problem of estimation? So given that we don't have any information about the characteristics of population, or more precisely about the parameters of the population, what we do, we basically assign the values of the true value of the, we basically assign the sample statistics as an estimator of the population parameter. Okay, so through the observation of the sample, we basically calculate the sample statistics, and that sample statistics is assumed to be a proxy for the population parameters. Okay, so that means we are here, what we are doing here, we are basically doing the estimation. Okay, the second part is more important. So after the estimation, that means you have done your estimation about certain population parameter, be it population mean, be it population variance, population median, population standard deviation, whatever estimation you have done, that is a sort of a claim, right? So you are basically claiming on certain characteristics of the population. So it is basically, so you are basically setting some hypothesis about the population parameters. Now, it is very important because your hypothesis is subjective. Why it is subjective? Because you are claiming that this is the true value of the population from drawing a sample, or which you are claiming that is a representative sample. Somebody else can also draw another set of samples from the same population and claim that this is my this is the estimation, which is the true value of the, which is the estimation for the true value of the population parameter. So it can vary from one researcher to another. Now, how you validate, how you statistically validate the hypothesis in the light of the information which are provided by the sample is something which is in the domain of hypothesis testing. Okay, so the procedure which enable us to decide whether a certain hypothesis regarding the population parameter is accepted or rejected is called the test of hypothesis or test of significance. So first we do the estimation about some population parameter through the study of the sample statistics, and from this estimation we set a claim, or we set some hypothesis about the population parameter, and then we statistically validate that claim through the hypothesis testing. Is it clear? Is it clear? Okay. So,
Yes, ma'am. Yes, ma'am.
Sorry?
Yes, ma'am, it's clear.
Okay. Okay. Now let us do one by one. So we will have to now understand the theory of estimation. Now, estimation again is consisting of two parts. One part is called the first one is called the point estimation. The second part is called the interval estimation. So what is these two point and the interval estimation? Let us do one by one. So suppose you have a random variable called x, and this x can have which you have drawn as a sample from a population. So the population involves some unknown parameter called theta. Okay, so the variable which you have, the sample which you have done, where one variable, suppose x is the random variable, which has say n observation. So your sample size is n, x1, x2, x3, xn. Okay, and from this observation of the sample, you are trying to estimate an unknown population parameter, which is theta. Okay, theta is not observable because entire population is not accessible to it. Okay, so therefore you are basically drawing a sample which is only a small subset of the population, and from the study of the sample you are trying to conclude about some population parameter. So it is required to find the estimate of the theta on the values of the sample, and the procedure involves these following steps. What are the following steps? First, you have to collect the sample. Now and you have to make the sample in such a way, that means you have to draw the sample in such a way so that it is the most representative sample. Okay, and then you have to collect the required information from the sample, calculate the values of the appropriate sample statistics. Okay, so from the sample statistics you assign the values of the corresponding population parameter. So this is basically the way you do estimation. And more it is, the step is in the involved step here is representing the point estimation. So the point estimation, as the term suggests, means that you are basically, through the observation of your sample, you are generating a single number as an estimate of the population. So it is called a point estimation. And the interval estimation, as the term suggests, here you are not generating a single number. Rather, you are constructing an interval and you are claiming that the true value of the population parameter must lie between these two intervals, and for which the researcher decides its own level of confidence. That means a researcher can be 99% confident, researcher can be 95% confident, researcher can be 90% confident. So these are conventionally the level of confidence which the researcher can set in order to estimate, in order to draw the interval estimate of the true value of the population parameter. Okay, so okay, so as I already said, that the point estimation basically generate a single value. Okay, the value of the sample statistics that are needed to estimate the population parameter is called the point estimate. Here the estimate value is given by the specific numerical figure. It's a single number, which is a function of the sample statistics. This is important. Why it is a function of the sample statistics? Because as you draw your sample, suppose you have a population of say 10,000 and you have drawn a sample of say 500. Now, from this 500 sample, you are calculating the sample statistics and claiming that this is the point estimate of the true value of the population parameter of the 10,000 the population of which size is of 10,000. Now, in that case, as you keep on changing your sample, that means you may just do one way is that if you keep the sample size same, but you just repeat these drawing of the sample. Okay, so so each time you are drawing the sample, each time you are generating a sample statistics from that. Okay, now these sample statistics are not necessarily supposed to be equal, even though you are fixing the size of the sample. That means suppose your sample size is fixed at 500, but you are doing a repeated sampling. Okay, that means you are doing a repeated trial of drawing samples of 500 from a population of 10,000. Now, each time the sample statistics which you are getting are not necessarily same. They are keep on changing. Okay, now in that case, it is therefore called a function of the sample observation. If you increase the sample size, your sample statistics will be more and more closer to the population parameter. If you even keep the sample size same, your sample statistics are not supposed to be same in all the repeated draws. Okay, so therefore it is a function of the sample statistics. The function is called the estimator of the parameter, and the value, the single value which you generate, is called the estimate. So the difference between the estimator and the estimate, please, should be remembered. Okay, now obviously when you are estimating a single number and claim it as a point estimation, there will be as sample, given that the sample is very small subset of population, it is not supposed to be coinciding with the true value of the population parameter, and in some way it may differ from it. Right? So in that case, whenever we use point estimation, we also calculate the margin of error. So what is margin of error? Margin of error is basically calculated by, say, for the Z distribution or the standard normal distribution. It is something like that. You have to take the standard error. Standard error, if you remember, is the standard error is the standard deviation of the sample, which is sigma x divided by root over n. This term, sigma x divided by root over n. And what is this 1.96? If you recall, we discussed about some of these numbers when we discussed about the Z distribution. If you recall that we said that if you take plus minus 1.96, the area of the standard normal distribution beyond plus 1.96 and beyond minus 1.96. That means the area which is below the extreme ends of the tail of the Z distribution or standard normal distribution is 5%. That means the area within the plus minus 1.96 is actually 95%. Okay, so if you want to have want to be confident at 95% level, you may have taken 1.96 into sigma by root over n, which is your standard error. If you want to calculate the margin of error with a confidence of say 99%, instead of 1.96, you could have taken 2.58. That is also another number which I mentioned the last class, that you should remember this number 2.58. If you take plus minus 2.58, between this plus minus 2.58, the area under the standard normal distribution is 99%. That means the area beyond plus 1.96 and the area beyond minus 1.96 together constitute of 1%. Okay, 1%, and given that the standard normal distribution is a symmetric distribution, so obviously the area to the left of the extreme end of the tail of minus 1.96 ordinate value and plus 1.96 ordinate value should be equal, which is 0.05% in the left hand side, 0.05% in the right hand side, which means, sorry, 0.005% in the left hand side, 0.005% in the right hand side, together constitute 1%. That means the inside the area it is 99%. Okay. So the criteria, again, I would like to not spend time because I will not be able to finish what I'm supposed to finish in this class. So I'll just keep this information. You remember that 95% it is the 2 standard deviation, 99 for the 0.74% for the 3 standard deviation, and then we discussed about this plus minus 2.58 is 99%, plus minus 1.96 is 95%. Okay, so I'll just keep. I thought that I should keep this. You need, I can. I think we will go now directly to the interval estimation. Okay. Now let us discuss about, so we discussed about the point estimation, we discussed about the discrepancy between the sample statistics which you claim as an estimator of population parameter, that discrepancy is to be allowed. You cannot expect that your estimation is 100% precise. That means your estimation is exactly equal to the true value of the population parameter. Why? Because you are drawing or concluding your estimation from the observation of the sample only. Okay, and therefore some degree of the margin of error should be exercised during the point estimation. What is that degree of margin of error? That is under the discretion of the researcher. That means if the researcher want to be 99% confident, then it is basically 2.58 into sigma by root over n, which is where your sigma by root over n is the standard error of the sample or the standard deviation of the sample. Now, the next part is the theory of the theory of estimation is the interval estimation. So in the interval estimation, as I already said, that instead of generating a single number as we have done in the point estimation, we basically construct 2 intervals, and these 2 intervals, and therefore we claim that the true value of the population parameter, which is unknown to you, must lie between these 2 values of the 2 intervals, and for that you are some percent confident, be it 99%, be it 95%, like that. So in that case, let us consider some unknown population parameter theta. And let us consider a sample of size n, which is drawn from the population. Okay, so the sample observations are like this: x1, x2, x3, xn. Now, based on the sample observations, we will be trying to find out two numerical values, which are the two intervals. Okay, let it be T1 and T2, such that the probability of the true value of population parameter theta being included in the interval T1, T2 is given by some value, say C. So we call that the probability, P is a probability that theta lies between these two intervals T1 and T2 is equal to C. Okay, so what we are doing here, we are constructing, instead of a point estimation, we are constructing two intervals, and we are claiming that the true value of the unknown population parameter must lie between these two intervals, and for which we are C% confident. It can be 99%, it can be 95%, it can be 90%, which are conventionally fixed. So it is P means probability that theta, which is your population parameter, lies between the two interval T1 and T2. And this probability is equal to some C. Okay, so such an interval is called the confidence interval for theta. T1 and T2 are the two quantities which are used to specify the intervals, are known as confidence limit. And the probability C with which we are confident, we are setting the confidence interval, will include the true value of the population parameter, are called the confidence coefficient. Okay, so if you just estimate the population mean, so your parameter is the mu, which is the population mean. And in that case, you are interested to find out the interval estimation of the true value of the population mean mu. Okay, so in that case, I'm not going through all these calculations, but I'm just saying that suppose, given that it is an estimation of the population mean, and given if your sample size is large and your sigma square, which is a variance of the population, is known to you, the standard test which is used, called the probability distribution, which is assumed, is the normal distribution or the standard normal distribution. So I'm repeating once again, I'm saying if it is a test for population mean, so test for population mean, as you know that mu is the notation conventionally used for the parameter which is mean in the population. So if the test involves the estimation of the population mean mu, in that case, the probability distribution which is to be assumed is the standard normal distribution, which basically means you can convert it into from x variate to z variate. That means standard normal distribution. Okay, so if it is a standard normal distribution, you remember the mean is 0 and the sigma square is the variance is 1. Okay, so that is the standard assumption about the probability distribution. But mind it, if it is, had it been the variance, the standard normal distribution is not the appropriate probability distribution to be assumed. Rather, chi-square is another probability distribution which is to be assumed. So depending upon which parameter you are going to test, every time the researcher must think and take a call on the probability distribution before doing the interval estimation. Okay, so here we are doing the test for population mean. So the appropriate the probability distribution is the standard normal distribution, and we are basically saying that the true value of the population parameter must lie between these two intervals. So how the intervals are constructed, the calculation part is here very easy, not at all difficult, but only the inequality, how the direction of the inequality gets changed if you transfer the denominator to numerator or negative value to positive value. Those things are to be basically understood in order to do that. But given the time constraint, I would like to just highlight the main part of the estimation and hypothesis testing. So it is basically for the 95% confidence interval, we basically take the point estimate, X bar, because we are constructing the confidence interval for the population mean. So what is the point estimate for the population mean? The sample statistics, which is X bar. So we are taking the point estimate plus minus, what is this? This is basically your margin of error. So when you are adding and subtracting the margin of error, because we remember when we are discussing about the point estimation, we say that some degree of margin of error should be exercised in order to estimate the point estimates. Why? Because the point estimate is just a single number, and it's a very risky business to conclude about the true value of the population parameter just from the observation of the sample and the calculation of the sample statistics. So we allow certain margin of error, and that margin of error is under the discretion of the researcher. That means at what degree of confidence you should allow the margin of error is to be decided. Okay, so this margin of error has to be included in order to construct the confidence interval. So in that case, 95% confidence limit is constructed by taking the point estimate X bar plus minus 1.96 sigma by root over n. So you can understand now there are two values. One is X bar minus 1.96 sigma by root over n, that gives you the lower interval, and X bar plus 1.96 into sigma by root over n, that gives you the upper interval. Okay, so these two intervals are constructed so that the researcher can claim that the true value of the population parameter, which is here mu, should lie between these two intervals, and for which the researcher is 95% confident. Okay, so instead of 95% confident, you may set the confidence limit at 99%, and in that case your confidence intervals become point estimate X bar plus minus, now instead of 1.96, it is now 2.58. Okay, why 2.58? If you recall the Z distribution, plus minus 2.58, you have 99%. The area under the standard normal curve between plus minus 2.58 is 99%. So beyond plus 2.58 or to the left of minus 2.58 together constitute only 1%. Okay, so if you want to be 99% confident, your interval estimation gives you two values. One is X bar plus 2.58 into sigma by root over n, X bar minus 2.58 into sigma by root over n. What is this sigma by root over n? It is nothing but the standard error which we discussed in the last class. Now, if you want to be almost sure, in that case, it is instead of 1.96 or 2.58, it is 3. Because standard normal distribution within plus minus 3, if you recall that most of the observation is supposed to lie. That means the probability is 99.74. That means beyond plus minus 3, only very, very minuscule observations are likely to lie. Okay, so it is if it is in case of the almost sure the confidence limit of the mu, it is X bar plus 3 into the sigma by root over n, which is your standard error. Since 99.73% of the area of the standard normal curves lies between the ordinate value of Z plus minus 3. Okay. Now I'll just help you to understand this with the example. So this one is saying that a sample of 10 observations are drawn from a normal population with unknown mean and variance. Just give me one time. Variance of 44.1 square inch. So what is given to you? Mean is unknown. Your sample size is 10 and 44.1 is basically the variance of the population, sigma square. Okay, so you can easily calculate the standard error, sigma by under root of sigma by root over n. Sorry, sigma by root over n. Root over n is root over 10. Okay, sigma is under root of 44.1. Okay, so if and the observation, these 10 observations which are your sample is basically given to you 65, 71, all these values. Now, if you have to obtain the 95% confidence interval for the population mean, what you have to do, you basically have to calculate the sample statistics from these 10 observation, which is nothing but summation xi divided by 10. So which comes out to be 73.8. Now you have to construct the confidence interval, which is at say 95%. So it is the, if you recall the formula, it is the point estimates, that is the sample statistics x bar plus minus 1.96 into sigma by root over n. So sigma squared is given to you. So the under root of 44.1 divided by root over n, which is under root of 10. Into 1.96, this value gives you the margin of error, and this is your point estimate. So you get two values. One is basically 77.91 and another is 69.69. 69.69 is that lower interval, 77.91 is the upper interval. And what is these two intervals tells you? The two intervals tells you that the true value of the population mean mu should lie between these two intervals, and for that you are 95% confident. Okay, if you wanted to construct 99% confidence interval, for that what you have to do, instead of 1.96 you have to take 2.58, and then the rest of the calculations are exactly the same. Okay, so you are now understand how to construct the confidence interval in case of the unknown population parameter, which is your population mean mu. Okay, so here the formula is like that: x bar minus z alpha by 2 sigma by root over n. Sigma by root over n is your standard error. X bar is your population mean, and mu is the unknown population mean. X bar is your sample statistics, sample mean, and mu is your unknown population mean. But what is your Z alpha by 2? Z basically means the probability distribution followed. Here is the Z distribution, and alpha by 2. This alpha is called the level of significance. We will get to know about alpha more clearly when we will start the hypothesis testing. But for the time being, just understand this alpha basically decides how much confident you would like to be. That means if you are 99% confident, in that case your value of the alpha is 1%. Okay, and given that you are constructing two intervals and the Z distribution is a symmetric distribution, you divide the alpha into two equal parts, one in the left hand side, another in the right hand side. That means for 95% confidence interval, your alpha is 5%, which you would like to divide 2.5% in the left hand side, 2.5% in the right hand side. So depending upon what alpha you are trying to construct, the confidence interval decides your Z alpha by 2. That means if you want to be 95% confident, your alpha in that case is 5%. So your Z alpha by 2 is basically, you want Z of 2.5%, 0.025 in the left hand side, Z 0.025 in the right hand side, which basically means 1.96. Okay, but if you want to be 99% confident, your alpha now is 1%. So you would like to get a Z alpha by 2, which is Z of 0.005, which is 0.5% in the left hand side, 0.5% in the right hand side. So your Z alpha by 2 now becomes 2.58. Okay, so the term sigma by root over n is called the maximum error estimate, which we already discussed. It is the maximum likely difference between the point estimated value of the parameter and the true value of the population parameter. Okay, so the likely difference between the point estimates and the true value of the population parameter is captured by the maximum error estimates. Okay. Now there is another distribution which is called the T distribution, which I would like to give very briefly, because when we will discuss about the hypothesis testing, both the Z distribution and T distribution both are used in case of the test for the population mean, okay, depending upon certain condition. What is the condition? As I already said, that in case of the point estimation or interval estimation for the population mean, we will use Z distribution if our sample size is pretty large. But if your sample size is small, in statistics, small sample size is basically described wherein your sample size is less than 30. Okay, if you have a small sample size and the information about your population standard deviation or population variance is not known to you, you cannot use Z test. You have to use then T test. Okay, so in that case, if you remember, if your sample size is pretty big, you don't have to bother whether you have information about the population standard deviation or not. You don't have to bother. You can estimate the population standard deviation by taking the sample statistics of sample standard deviation. But if your sample size is small, that means less than 30, in that case, if you don't have the population standard deviation, in that case, you cannot use Z test. Rather, you have to use T test. And T test or the T distribution, you have to use the probability distribution, which is the T distribution. Now, what is the type of probability distribution? Obviously, this is also PDF, probability density function, like the Z distribution or normal distribution. Okay, because your X can take X is basically a continuous variable. So X can take infinite number of values within two intervals. Okay. Now, what is the probability density function looks like for the T distribution? This is looking like this. Okay, where your T value, that is the ordinate value, must lie like the standard normal distribution and normal distribution between minus infinity and plus infinity. Okay, so it is similar to normal and the standard normal distribution in many ways, like the two lengths of the tail of the T distribution stretches towards minus infinity and plus infinity, and they don't touch the x-axis. The distance between the x-axis and the tails of the T distribution becomes smaller and smaller and become negligibly small, but it should not touch the x-axis or T values, T axis here. So this property is called the asymptotic property. Yeah? And it is a symmetric bell-shaped distribution like the standard normal distribution or normal distribution, and it is symmetric about its mean value. That means mean is equal to median is equal to mode, because it is a symmetric distribution, and these mean, median, modes all are located in the centralmost. The curve never touches the x-axis. So in case of the T distribution, the confidence interval for the mean is to be calculated. The concept is exactly the same. The confidence, that means the interval estimation and the point estimation, that holds good for the T distribution as well. But only difference here is that if you look at this formula for the confidence interval here, this is your unknown population mean mu. And you have two values in the left-hand side. This is the lower interval. In the right-hand side, this is the upper interval. Okay. But, and what is in the lower interval tells you this is your point estimates. This is your standard error, S by root over N. Given that sigma, that means the population standard deviation is not known. You are estimating it by taking the sample statistics for standard deviation, sigma by root over. And same way here also point estimation plus this is your margin of error. But T alpha by 2 here and T alpha by 2 here is not exactly the values which under the standard normal distribution, you know the values basically depending upon at what level of confidence you would like to construct your confidence interval. That means if you want to be 99% confident, you know the value is 2.58. If you want to do the 95% confidence, your Z alpha by 2 is 1.96. So these kinds of values you know. But in the T distribution, this is not supposed to be known to you. You have to go to the table to look at the T values, okay? And the trick here is that here the T distribution is not just like the C distribution. T distribution is characterized by the degrees of freedom. What is degrees of freedom? Degrees of freedom in the T distribution is nothing but n minus 1. N is the sample size minus 1. So when you will be looking at the T table, you will be finding that the first columns gives you the degrees of freedom. And then you have the alpha value. That means level of significance. If it is a 2-tailed test, 1-tailed test, these values are given to you, and then corresponding ordinate values of the T are given to you. But remember it that T test is, as I said, if it is a small sample, then only your PDF is to be considered is the T distribution. But if your sample size increases, T distribution actually converges with the Z distribution. So in the T table, when you look at the T table, I've shared the tables. So you will find that the most of the T tables which are available in the net or in the book, T table values are given till up to 30 or 28 in many books. Okay, why it is so? Because beyond that, your T distribution is converging with the Z distribution. So there is no need to give the T value. Don't have to do. If you have a big sample size, you basically don't have to consider the, look at the T table, find out for the respective degrees of freedom, your T alpha by 2. That is not required. And if you recall that during the regressions, when you have run the regression, your Stata output or your SPSS output gives you a T value, your coefficient value for the regression, and then the standard error, and then there is a T value, and then the corresponding P value is given, and after that the interval estimates are given. The coefficients are basically the point estimates of your respective regression coefficients, and the interval estimate is given in the extreme right side of the data output. Okay, now these coefficients, these interval estimates, the Stata by default give you at 95% level of significance. Okay, so 95% confidence level. Now you may ask that why the T table T values are given to you. Even though most of us in economics, we don't work on small samples. Our sample size are most of the time, it is more than, it is a large sample, okay? But why T? Why the T distribution? Why not the Z values are given to you? It is basically to take care of the small and the large, but generally your T values are basically, you don't have to go to the table for going for the looking at the T values, like for the respective degrees of freedom. So suppose your N is say 50,000, your sample size is 50,000, and suppose you have run a regression with say 3 or 4 variables. Okay, your explanatory variables are 4, along with the interceptor you have 5 variables. Okay, so your degrees of freedom is N minus 5. Okay, now in that case, will you go to the T table and look at the N minus, that means 5,000, what I say, 50,000 minus 5 degrees of freedom, what is the respective T value to take a call whether your respective regressions are, the coefficients are significant or not? This is not at all required, because the rule of the thumb is that if your T value is greater than 3, just remember, because your standard normal distribution, absolute sense, T value can be negative, it can be positive. We are not bothered about negative or positive for taking a call on the significance. We just take the absolute value of the T and then we conclude whether it is significant or not. And the rule of the thumb is that if it is more than 3, you recall that the maximum value of the standard normal distribution, between which the most of the 99.73% of the of the population are samples are likely to lie. So in that case, your plus minus 3 means that it is most likely that your test statistics will do the hypothesis testing, and then I'll explain again that your test statistics will lie in the critical region. Okay, so in that case, these T values are only important when you will be explaining in the class, but when you will do your own research, these T values are not so important. We go by the rule of thumb. Because your T distribution, when your sample gets larger, T distribution converges with your standard normal distribution. Okay. Now, these are basically when to use z-test or t-test. These are the rule of thumbs which are given to you. And I've already said that if your sigma, which is your population standard deviation, is known to you, you don't have to add the variable is normally distributed. And if your n is even, the small sample less than 30, still you can use z-test. Okay. If sigma unknown, the variable is normally distributed and it is a large sample, you use z-test. But when you use t-test, if sigma is unknown and the sample is a small sample, you cannot use z-test. Okay, so these are the rule of thumb. So I am leaving these things. I can't have that much luxury of just taking many things in this 90 minutes class. So I'll just now go to the hypothesis testing. Okay? So this is the second part of the inferential statistics. So what the hypothesis testing tells you, it is basically when you are doing a hypothesis testing, you recall in the beginning I said that you have done some estimation about the true value of the population parameter from the observation of the sample. But these estimations are subjective because it keeps on changing according to your sample size, and also the composition of the samples. So in that case, you have to statistically validate your claim on the estimation. And for that, you can use the tools of hypothesis testing. So in the hypothesis testing, therefore, is a kind of a conjectural statement about how the variables are related. You can discuss some relationship about the population parameters. So it is a formal statement that presents the expected relationship between an independent variable and a dependent variable. It's a crucial step in the scientific method and therefore critically important for all scientific research. Please remember that even if you do a qualitative study, then also the hypotheses are to be constructed for any meaningful scientific research. Why? Because your objective, when you are constructing or formulating your objective may looks to be very broad. If you have to narrow down to certain variables, you have to convert it into hypothesis. Therefore, your hypothesis testing basically helps you to formulate certain claims or assumption about one or more population parameters. Okay. So the hypothesis testing is always about the population parameter. Please do remember it has nothing to do with the sample statistics. Okay, the procedure that enables us to decide whether a certain hypothesis is to be accepted or rejected is called the test of significance or the test of hypothesis. Sample evidence is used to assess the probability that the claim about the population parameter is true. And as I already said, both qualitative and the quantitative research involve formulating a hypothesis to address a research problem. And in the first step towards the formulation of the hypothesis basically starts with identifying the research objective. You narrow down the research objective towards a certain hypothesis, which is a claim about certain population parameter. A problem cannot be scientifically solved unless it is reduced to the hypothesis form. Thus, it is a very powerful tool in the advancement of the knowledge, consistent with existing knowledge and the conducive to further inquiry. Now, for the understanding the hypothesis testing, we have to now understand some of the concepts which are critically important to understand the hypothesis testing. What are these? Now, these are basically the null hypothesis, alternative hypothesis, level of significance, critical region, decision rule, type 1 error, type 2 error, one tail test, two tail test, one sample test, two sample tests. So we will do one by one. Okay. So null hypothesis and alternative hypothesis. So when you do the hypothesis testing, first thing is to formulate two mutually exclusive statement about your population parameters. Okay, so the one is called the null hypothesis, another is called the alternative hypothesis. These are two mutually exclusive and exhaustive statement. Why they are mutually exclusive and alternative statement? Either in the null or in the alternative, you set your claim. You may have some estimation which you have done about through the sample observations. You may set your claim that the true value of the population parameter is this. That means your sample statistics is equal to the true value of the population parameter in any of these null or the alternative. And then you refute the claim in the other. That means if you set the claim in the null, that your x bar, which is your sample statistics, is basically equal to mu. That means the true value of population mean. Okay, that's your claim in the null. Okay, so when you are claiming in the null, in the alternative, you have to refute the claim, and that's why they are mutually exclusive and exhaustive statements. Okay, so when you are refuting the claim in the alternative, it can be both ways. That means if this claim is not correct, right? That means mu is not equal to your sample statistics x bar. In that case, it can be that your mu can be greater than x bar. It can be that mu can be less than x bar. But as a researcher, you are not sure. So in that case, you can set the alternative hypothesis by saying mu not equal to x bar. Okay, so when you are saying this is basically counteracting or refuting your claim which you set in the null. Is it clear? Is it clear? Is it clear to all of you? Or
Yes,
am
ma'am,
I
yes.
audible?
Yes, yes.
Okay, okay. Now in the null and the alternative hypothesis, H naught is a statement about some population characteristics, and how we do that, we begin the assumption that the H naught is true, and then any difference between the sample statistics and the true population parameter, we assume that it is basically because of the chance and not a real difference. Okay, and the observed value of the test statistics will generally differ from the expected value because of the sampling fluctuations. Because with the same sample size, if you keep on drawing the sample from the same population, you may not get the same sample statistics. So that means that because of the sampling fluctuation, your sample statistics may vary, and the observed difference between the true value of the population parameter and the sample statistics may be due to the sampling fluctuations. The sample is analyzed to decide whether to reject or accept H naught if the difference is very large. So in that case, H naught is rejected. But if the difference is not so large, then H naught is accepted, and the difference is considered to be because of the sampling fluctuations. Now the question comes, when you will consider the difference is very large, when you will consider the difference is not that large, that is basically to be understood through the understanding of hypothesis testing. Okay, so it is therefore necessary how much of the difference is tolerable before we conclude whether H naught is to be accepted. Okay, now what is the alternative hypothesis? It is just the opposite of the null. That means, as I said, that suppose that the average rainfall of certain city in India in the wettest month is, say, 3 to 8 millimeters. So you are setting this in the null, and in the alternative, you are refuting that claim. That means by saying mu not equal to 3 to 8 millimeter. Okay. So remember that null is always conventionally written as H naught, and the alternative is conventionally written as H1, right? And it is general that the hypothesis the researcher is trying to prove, evidence always examine that the respect to H1, never with respect to H2. So the steps are basically like this. We have to develop the null and the alternative, then specify the level of significance, which you remember is alpha. Now we will try to understand what is this alpha. So we basically reject or accept the null hypothesis based on certain alpha. Alpha actually is the area under the respective probability distribution which defines the critical region. Critical region is what? It is also called the rejection region. Okay, so and it also depends upon whether it is a two-tailed test or one-tailed test. Okay, so the alpha is in just for the time being, please understand that alpha defines the critical region or the rejection region. So that means if your test statistics, we have to construct the test statistics. If your test statistics lies in the critical region, we reject the null hypothesis. If your test statistics lies in the acceptance region, which is in between the we will discuss. We will show that I'll show you the diagram, then it will be much easier to understand, which is called the acceptance region. So if it lies in the acceptance region, we cannot reject the null hypothesis. Okay, so the step 3 involves collect the sample data and compute the value of the test statistics. So we have to calculate the test statistics to do the hypothesis testing. Now, hypothesis testing again can be done in 2 ways. One is called the rejection region or the critical value method. Another is called the p-value method. Okay, so then the rejection region method, it is basically you have to compare 2 values. 2 values in the sense, one is your test statistics, which you have calculated from the sample observation. Another is your tabulated value, which you can draw from the tables of the respective probability distribution. Okay, so the tabulated value in the case of the Z distribution, if it is a case of population mean, the parameter is population mean. So in that case, and you are setting a claim in the null or in the alternative about the population mean, in that case, your underlying probability distribution is a Z distribution or T distribution. So if it is a Z distribution for a large sample size, in that case, your alpha is set according to the acceptance region. How will be your acceptance region? If you want to be 99% confident, your alpha becomes 1%. That means your entire critical region is 1%, okay? Or rejection region is 1%. If you want to be 95% confident, your alpha is then 5%, okay? So we will try to explain, I'll try to explain this thing much more rigorously in the subsequent slides. You have to hold me for some time. So we basically calculate the test statistics and then use the level of significance to decide the rejection region or the critical region. And then we compare the 2 values. One is a tabulated value and another is the test statistics value. If your test statistics value is greater than your tabulated value for a plus value, and if it is less than the tabulated value for the minus value, your test statistics is supposed to lie in the critical region and you cannot accept the null hypothesis. You have to reject it. But in the p-value method, you have to do one more extra step. That means instead of comparing, please pose your question.
Madam, one small doubt regarding this p-value and critical value approach. So how we have to decide this p-value and critical value? Can you elaborate on it?
Voice is getting blurred. Can you please little louder?
Madam, regarding p-value and critical value.
Yes.
Can you elaborate how we have to decide?
I will do that. Don't worry, I will do that. It is just to help you to understand the steps. I will do the p-value method and the critical region method one by one. So So in the p-value method, you have to do one more extra step. In the critical region method, you are only comparing the ordinate values, like the one is a tabulated value, say for the z distribution. For the z distribution, say you have 1.96, 2.58, these values are to be compared with your test statistics. That means you are comparing the z value or the ordinate. But in the p-value method, you are comparing with the alpha. That means your level of significance and the p-value. You have to find out the p-value from your test statistics by using the standard normal distribution table or T table, whichever is applicable. Okay. So I'll just go to the level of significance. So the maximum probability of committing the type 1 error is basically your alpha, which actually decides the level of significance. What is type 1 error? What is type 2 error? Just be patient. 1 minute. I'll come one by one. And then the level of significance is also the critical problem of choosing between the null and the alternative. The higher the level of significance, the higher is the probability of rejecting the H0, and it also defines a risk the researcher is willing to take of rejecting the null hypothesis. So I think I will now go one by one. So here we will first try to explain the one-tail test and the two-tail test before we go for the critical region. Okay. So what is one-tail test and two-tail test? Okay. So first is that consider the lower tail test or left tail test. Okay. Left tail test is basically where the researcher is very confirmed that his test statistic, his estimated value is suppose mu naught. This is the estimated value. Okay? And the true value of the population parameter is mu. And suppose that the researcher knows that the true value of the population parameter is less than these mu naught, which is a stipulated or specified value. That is the claim which the researcher is willing to make. Okay? Then the researcher has to refute the claim in the alternative by saying mu greater than equal to mu naught. Why? Because if the mu is not less than mu naught, what are the other possibilities? One can be that mu is equal to mu naught. Another possibility is that mu greater than mu naught. So when you are constructing your null and the alternative this way, you are basically making these two statements of H0 and H1 mutually exclusive. Okay, so it is a claim is now set in the alternative and refuted in the null. Now given that you are claiming that mu less than mu naught, you are expecting your test statistics will lie in the left hand side of the tail of the z distribution. Okay, so in that case it is a left tail test. Okay. Now, if you take the upper tail or the right tail test, here the claim, the null and the alternatives are set like this. Here the researcher is having some impression that mu is greater than mu naught. So this is the claim which the researcher is willing to make. So if the researcher has to construct the null, in that case, the researcher has to refute the claim which is set in the alternative by saying that mu less than equal to mu naught. So you can understand if mu is not greater than equal to mu naught, in that case, mu can be equal to mu naught or mu can be strictly less than mu naught. If you combine these two, it is your null is now mu less than equal to mu naught. And now you look at given that your alternative is mu greater than mu naught, you may expect that your test statistics will lie in the right end of the probability distribution. Here, it is the z distribution. Okay. But if it is a two-tail test, in that case, what will happen? You are setting your claim in the null by saying, say, mu equal to mu naught, but you are refuting the claim. You are not very much sure whether mu greater than mu naught or mu less than mu naught. So you refute the claim in the alternative by saying mu not equal to mu naught, keeping the possibility of mu greater than mu naught, mu less than mu naught. So this kind of test is called two-tail test. Why? Because you may expect your test statistics to lie either in the left-hand side or in the right-hand side of your respective probability distribution. Whereas in the case of the left tail test or in the right tail test, which is called one tail test, in that case, here in the left tail test, you are sure that your test statistics are, you are assuming that your test statistics will lie in the left side of the tail of the respective probability distribution, here Z distribution, whereas here you are expecting or assuming that the test statistics will lie in the right side of the tail of the Z distribution. Okay. Now diagrammatically look at these two tail and the one tail. This is the example of the two tail test. Okay. And this is your probability distribution. Okay. So this is your Z distribution rather. Okay. Now suppose your alpha is 5%. What is alpha? Alpha is the level of significance. And what is alpha? I said alpha defines the critical region or the rejection region. Okay. So this alpha 5% and it is a two-tail test. What does it mean? That your alpha of 5% has to be divided equally between the two ends of the tail of the Z distribution. Why? Because your Z distribution is a symmetric distribution. So 2.5% of the alpha will be in the right hand side. 2.5% of the alpha will be in your left hand side. Okay. So alpha by 2 here, alpha by 2 here, and it is a Z distribution, right? So it's a symmetric distribution. You have 0 here, and you recall that plus 1.96 minus 1.96, if you take these two values, then between this minus 1.96 and plus 1.96, you have 95% region under the Z distribution. Okay. So this region is called the acceptance region. That means what is measured in the x-axis? Your Z value, the ordinate values, right? So if your test statistics, we will now do one by one. If your test statistics lies in this region, that means if your test statistics lies in any of the ordinate value between minus 1.96 plus 1.96, you are basically in the acceptance region. So you cannot reject your null hypothesis. But if your test statistics lies here or here, because in the two-tail test, you are not sure whether your test statistics will lie in the left-hand tail of the probability Z distribution, which is your Z distribution, or in the right-hand tail of the Z distribution. So you have kept mu not equal to mu naught. So your test statistics may lie here or here. So if it lies in any of these critical region or the rejection region, you reject your null hypothesis at 5% level of significance. Now remember that if it is instead of 5%, if your alpha is, sorry, if you, just write it. Sorry. So if your alpha is 1%, that means 0.01. Okay. So in that case, mind it, your two value of the Z distributions are not 1.96. Now this one will be minus 2.58 and this one will be plus 2.58. Okay. And this area, this rejection area is not 2.5%. Now this alpha by 2 is basically, alpha by 2 is here 0.005, which is 0.5%. And this alpha value will be also, alpha by 2 is also 0.005. Okay, it is equally divided between the two ends of the tail of the Z distribution. Now you can see that if your test statistics lies in the rejection region, you reject the null hypothesis. If it lies in the acceptance region, you accept the null hypothesis. Now we will discuss about the one tail test. One tail test can be two types. One is a left tail test, another is a right tail test. And you would see that in the case of the left tail test, we have taken the null and the alternative like this. So here, remember, whatever alpha you are taking, alpha can be 10%, alpha can be 0.055%, alpha can be 0.01, alpha can be, that means 1%, or alpha can be 0.10, that means 10%. Whatever alpha you take, these are the conventional level of alpha, which is your level of significance. So here, given that it is a one tail test, be it a left tail test or right tail test, your entire rejection region or your critical region will lie in one end of the tail of the probability distribution or the Z distribution, right? So if it is suppose 5%, your alpha is 5%. In that case, what will be your rejection? And it is a left tail test. So in that case, you are expecting that your critical, your test statistics will lie in the left end of the tail. And therefore, your critical region, this is your rejection region or critical region, will lie to the entirely on the left-hand side of the tail of the Z distribution. Okay, so this is your alpha, which is, it is not to be divided now, 0.055%. And what is this value? Which is 1.68. What does it mean? This area is 5%, but entire area, this area is 95%, which defines your non-rejection or acceptance region. That means if your test statistics lies here, 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 you have to accept your null hypothesis. But if your test statistics lies somewhere here, you have to reject your null hypothesis. Now come to the right tail test. So in the right tail test, your test statistics should lie in the right end of the tail of the null probability distribution, because your mu is greater than mu naught is your alternative. Okay, so in that case, instead of left hand side, your entire alpha, that means your critical region or rejection region, will lie on the right side of the tail of the Z distribution. So in that case, this is 5% say, and the entire area to the left of this value, which is here, this one is minus 1.68. Please remember, this is the negative value because this is 0, all the negative values to the left hand side. So, and this will be plus 1.68, plus 1.68. Okay, but if you want to have alpha equal to 1%, 0.01. So your critical region will be smaller now. And this value is, if you recall, it is 2.33. So here it should be minus 2.33. So as the minus 2.33. So you remember that as you reduce your alpha value, what will happen? Your critical region will be shrinking. Okay, and it is your ordinate values will be rising in absolute sense. That means 1.668 in the absolute sense, be it negative or positive, 2.33 in the absolute sense. Okay, so it will be rising in absolute sense because you are more away from the central value, which is your mean value of the Z distribution, which is equal to 0. Okay, so is it clear to all of you? Is it clear?
Madam. Yes, madam.
Okay, so now we will discuss the type 1 error and the type 2 error. So the type 1 error and the type 2 error are basically, if you look at this matrix, you will be able to see that these are basically the decision, whether to reject the null hypothesis or not to reject the null hypothesis. And you have two options, whether your null hypothesis is true or null hypothesis is false. Now I would request you to just to focus on this cell and this cell. So what you find that if you're taking these two possibilities, that means H naught is true and you are rejecting the sorry, I will ask you to focus on these two, this one and this one. So here, if you take this cell, so what are the two possibilities? Your H naught is false and you're rejecting H. So which is basically a correct decision, right? So this is a correct decision. Focus on this cell where your H naught is true and you are not rejecting H naught, which means also again a correct decision. But if you focus now on this cell and this cell, what are the possibility? Your H naught is true, but you are rejecting H naught, which is an incorrect decision, okay? But when your H naught is true and you're rejecting H naught, this is your type 1 error, okay, which is defined by alpha. So that means if you keep your alpha big, like 10%, okay, so obviously in that case, you are more likely to commit type 1 error, because if your test statistics lies in the critical region, you are supposed to reject your null hypothesis. That means 10% means your critical region will be more bigger. So higher will be the chance that your test statistics lies here. And in that case, you have to reject your null hypothesis, even though they are true. Okay. So this type of error is called type 1 error. The second type of error which can be also committed is basically your H naught is false, but you are not rejecting, you are accepting it. So this type of error is called type 2 error. So that means type 1 error is when we talk about p-value, critical region method, we basically focus on the type 1 error, which is defined by alpha, your level of significance. So your level of significance, mind it, decides the critical region, which will help you to take a call whether to accept or reject the null hypothesis. And conventionally, your alpha is 1%, 5%, 10%. And depending upon whether it is a two-tail test or one-tail test, you have to take a call whether your alpha is to be divided. That means in case of the two-tail test, you divide the alpha equally between the two ends of the tail of the probability distribution. But if it is a one-tail test, your entire alpha is in the left-hand side for the left tail test or the right hand side for the right tail test. But alpha at the same time also decides the magnitude of your type 1 error. That means if you take a big alpha, obviously in that case there is a more likelihood of committing type 1 error. That means your null hypothesis is true, but given that your test statistics lies in the critical region, you are rejecting the null hypothesis, okay, and committing type 1 error, okay. And that is the reason, if you recall, when you do regression, when you take a call about the significance of your regression coefficient, we would like to take the alpha value at 5% or 1%. 1% means highly significant, 5% moderately significant. But when we have alpha value at 10%, that means we are rejecting the null, the significance of your estimated point estimates of the regression coefficients are basically significant at 10% or 20%. These are not very much encouraged. We say that these are weakly significant. Okay? And why it is not encouraged? The reason being is that more or bigger the level of alpha, higher is the chance of committing type 1 error. Okay? Now, I will now discuss little bit about the p-value method. What you do in the p-value method, I'll just go quickly to the hypothesis testing part. Yeah, yes, I can take this one. So these are basically the three different types of the tail. These two are the one tail test. This is the two tail test. And we discussed about that in the left tail test, your alternative is mu strictly less than mu naught. And in the alternative and in the right tail test, your alternative is that mu strictly greater than mu naught. In the two tail test, you take the alternative as mu naught equal to mu naught. Now, after that, what is the next step? Next step is to calculate the test statistics. How you calculate the test statistics? The rule is that observed minus expected divided by the standard error. What is observed? Observed is basically your X bar because it is a test for population mean. So it is X bar. What is expected? Expected is you recall that I talked about the biasness yesterday, that expected value of X bar is equal to mu. That is the true value of the population parameter. So that is basically your mu, divided by sigma by root over n. What is this? This is the standard error. Okay. So observed minus expected divided by the standard error gives you the test statistics. Now, for the two methods, rejection region method and the p-value method. In the rejection region method, you take the value of the test statistics, compare it with the tabulated value, and then take a call whether to accept or reject the null hypothesis. Okay. In the case of the leptal test, if your test statistics lies in the critical region, that means left end of the tail of the Z distribution, in that case, your Z value, which is your test statistics value, is less than equal to minus Z alpha. You recall that if your alpha is at say 1%, it is 2.33. So if your test statistics Z is less than minus 2.33, suppose your test statistics is minus 3.8. So obviously minus 3.8 is less than Z alpha, which is minus 2.33, because negative value, bigger the negative value, lower they are, right? So it is your test statistics is lying in the critical region. You have to reject the null hypothesis. But if your test statistics is say minus 1.28, okay? So obviously in that case, for a given alpha of 1%, your Z is greater than Z alpha minus Z alpha. What is minus Z alpha? Minus 2.33. So in that case, clearly it is lying in the critical region. Or even if your test statistics is a plus value, say it is your Z is equal to 2.33. So in that case, the plus value is always greater than minus of 2.33. So it is lying in the acceptance region. So you cannot reject the null hypothesis. Okay. The same way you can interpret the upper tail test. For the two tail test, this is your test statistics. You have to compare with the tabulated value. But mind it, for the two tail test, you are expecting that your test statistics may lie either in the left hand side or in the right hand side of the sides of the C distribution, right? And depending upon your alpha, say your alpha is 1%. So in that case, your Z's, your tabulated values of Z, that means Z alpha by 2 and minus Z alpha by 2 and plus Z alpha by 2 are minus 2.58 and plus 2.58. So if your test statistics lies between minus 2.58 and plus 2.58, it is lying in the acceptance region. You cannot reject the null hypothesis. But if your test statistics lies to the left of minus 2.58 or to the right of plus 2.58, you are actually in the critical region or rejection region. So you can reject the null hypothesis at 1% level of significance. Okay. Now, talk about the p-value method. So in the p-value method, you have to do one more extra step. What is that extra step? Corresponding to the Z value, you have to get the corresponding p-value from the Z distribution. Okay. So the probability, the Z table. From the Z table corresponding to the Z test statistics, you will have a corresponding p-value. Now, the rule of thumb is that just 1 minute. Yes. So the rule of thumb is that if your p-value is less than alpha, it is for one tail test, please remember. P-value is less than alpha, you reject the null hypothesis. That means your p-value is lying in the critical region. But if your p-value is greater than equal to alpha, you do not reject the null hypothesis. Suppose, now I'm taking, say, suppose your p alpha is 5% and it is a left tail test, right? So, and your p-value is say 0.002 or 0.02, okay? So it is 2%. Alpha, it's a left tail test, so you don't have to divide alpha. Okay, your alpha is 5%. That means alpha is 0.05. And you get the p-value from the test statistics from the Z table that alpha is 0.02. So your alpha is, your p-value is less than alpha, 0.02 is less than 0.05. Okay, 2% is obviously less than 5%. So it is like you have to reject the null hypothesis at 5% level of significance. Okay, but if it is a two-tail test, right, in that case, your alpha has to be divided alpha by 2, right? So it is 2.5% now. But given that your p-value is 2%, so in that case, 2% is still less than 2.5%, you can reject the null hypothesis. But suppose your p-value is 0.03, okay? But your alpha is, it's a two-tail test, alpha by 2 is 0.025, right? So in that case, 3% is greater than 2.5%. So in that case, you cannot reject the null hypothesis. You have to accept it. So please remember the rule of thumb. And now I will help you to understand that if you take the theta value for your regression, okay? So you have the coefficient value, which is your point estimates of the regression coefficients. Then you have the standard error. Then you have the t values, and then you have the p values, okay? We don't have to go to the t values every time, look at the table, take the degrees of freedom, and then take a call whether they are significant or not. We basically look at the p value and decide whether that or respective regression coefficients are significant or not. How we do that? If you have a p value close to 0, you don't have to think anything. Close your eye and say that your respective test estimated value, that means regression coefficient, is highly significant, because whatever alpha value you take, be it 5%, be it 1%, your alpha p value equal to 0 or 0.0005. This is very, very small. So smaller p value means higher chance of rejecting the null hypothesis. So your estimate is highly significant. But if you get a p value of say 0.21, that is 21%, whatever level of significance you take, you have to accept the null hypothesis of H not equal to, your mu is equal to 0. So your estimation is not significant. So if you take the p values, that column, and you see that your p value is less than 0.05, so just close your eye and say that it is significant at 5%, okay? So, but if you take the p values, that means more it is closer to 0, higher is the chance that of rejecting the null hypothesis. That means your estimates are significant. You can take these hypothetical values. Suppose your p value is less than 1%, p value less than 0.01. So what will be your call? You obviously will be rejecting the null hypothesis at 1% level of significance, because your p value is less than alpha equal to 0.01. Okay. Now, if your p value lies between 1% and 5%, right? So suppose your p value is 0.025. Okay. So it is 2.5%. You reject the null hypothesis at 5% level, but you cannot reject the null hypothesis at 1% level, because 0.025 is less than 5%, but greater than 1%. So you cannot reject the null hypothesis at 5% level of significance, but you can reject the null hypothesis. You can reject the null hypothesis at 5% level of significance, but you cannot reject the null hypothesis at 1%. Okay. But if your p value lies between 5% and 10%, remember, this is a very risky proposition. You cannot reject the null hypothesis at 5%, because your p value is now greater than 5%. you have to reject the null hypothesis at 10%. And 10%, at 10%, if you reject the null hypothesis, you recall that you are likely to commit type 1 error. Your chance of committing type 1 error is very high because alpha 10% means higher is the likelihood of committing type 1 error. Okay. If your p-value is greater than 10%, do not reject the null hypothesis. The difference is not significant. I think if I can continue, but you people must be feeling very hungry and you have another session in the post-lunch. So if you have any queries, I can take a few queries, but I can be accessible through WhatsApp, through email. If you have any queries, please do ask me. I will be happy to respond to your questions. And I will be definitely sharing my lecture slides. Okay. So I think that I should stop here. And if you are willing, I can take a few questions. Hello? Hello?
Thank you, ma'am. Thank you so much.
So no questions? Hello? No questions from your side? I can understand that so many concepts are poured within a very short time. Things are difficult to understand, but given that these are actually taught in a it takes some weeks to basically explain and clarify the concepts, but just condensing it within 90 minutes is difficult for you to understand. That I clearly can feel. So I think that in case there is no question, I'll take your, I'll then make a move. I'll finish it here. Otherwise, I'll be happy to take a few questions. Hello?
Hello. Good afternoon, madam. This is Tirumalesh.
Good afternoon.
This is Tirumalesh, madam, lecturer in economics, Government College, Autonomous, Anantapur, madam. Hello.
Madam, is it audible, madam?
Yes, yes, audible, audible.
Madam, excellently. Madam has excellently enlightened us the topic about the estimations and hypotheses of testing, which play a vital role in selecting data, sample, and research work. On behalf of Commissionerate of College Education and lecturers of economics faculty, I sincerely thanks to madam. Thank you very much, madam.
Thank you so much. Be in touch. If you have any queries, please don't hesitate. I will be happy to respond to your clarification, to provide you clarification. Thank you.
Thank you,
Thank
madam.
you so much.
Thank you for
Thank you so much.
thank you for attending another session. Thank you, madam.
Thank you so much.